Hello, everyone. My name is Jakob van den Eijnden. I'm a Warwick Prize Fellow at the University of Warwick. And today I'd like to talk to you about what we can expect for accreting neutron star jets and studying these in radio with next generation facilities like the SKA and the next generation VLA. I will be talking about radio jets, and jets are, of course, a phenomenon that occurs all across the universe on a wide range of physical scales and that evolve on a wide range of time scales. Jets are also very important in affecting both the system that launches them and the direct surroundings of that system. Here you can see a couple of situations and a couple of environments where these jets are relevant. You can think of, for example, Eijnden. On the top left, you can think of GRBs, jetted TDEs, but also much smaller scales such as young stellar objects and forming stars. In order to study jets, one system that we can focus on in our own galaxy are X-ray binary systems. X-ray binary systems are in fact very useful to study jets, as their accretion flow and the jets that are launched from these accretion flows evolve on human timescales. So think on timescales from below a second up to weeks or months or years. X-ray binaries, if you would try and go and build one yourself, are basically made out of different parts, typically a compact object in an orbit around either a low or a high mass star. You can see this in the artist's impression, for example, in this slide here. And if the binary system is oriented and constructed in the right way, mass transfer will take place from this donor star onto the compact object. This takes the form of an accretion flow, and the inner parts of this accretion flow can launch jets, which tend to be dominant in the radio band. As I mentioned as well, the compact object in these systems are either black holes or neutron stars, and in this talk today, I will really focus on what we can learn from neutron star systems. Now, as I mentioned already, studying jets in X-ray binary systems has one very big advantage, which is that they change dramatically on humanly accessible timescales. They do so in response to changes in the accretion rate. And we can track that in these systems by observing them in different observing bands at the same time. These two observing bands are the X-ray band, because the X-ray luminosity tracks the accretion rate in these systems, and the radio band, because the radio band is a proxy for the jet power and the jet properties. If we do this for so-called low-mass X-ray binaries, so systems where the donor star is a low-mass star, we get the following points in this diagram here. You see a lot of different types of data points. The black circles here are systems with a black hole as the compact object. And you can see that these black holes show a coupling or a correlation between X-ray and radio luminosity. And this is indicative of a coupling between the inflow of material and the outflow in the jet. What you can also see is that at every given accretion rate, so every given X-ray luminosity, the black hole points are really the brightest radio points. And below that, in all these other different colors, you see neutron star low-mass X-ray binary systems. You can see that as a sample, these neutron stars also show this coupling, but they are radio fainter typically than the black holes. They have also been very poorly studied below about 1% of their Eddington accretion rate. And something you cannot see in this diagram is that they also tend to evolve more quickly through outbursts, which makes it challenging to study them in radio. If we also include systems where the donor star is a massive donor star, you can get the following picture in a slightly different version of this same diagram. In this version of the diagram, what you see in the colored points are three high-mass X-ray binary systems, so neutron stars accreting from a massive donor star. You can again see that they show a coupling between inflow and outflow, but these systems have been probed over an even smaller range in X-ray luminosity. And that's really the case because they are the radio faintest type of X-ray binary. At this point, you may wonder why we even bother studying jets with neutron stars and X-ray binaries. Why not just focus on these black holes and use them to make use of the advantages of studying jets and X-ray binaries? Well, that's because neutron stars offer a couple of additional properties that make them very interesting to study jets. The first is that these neutron stars have a magnetic field that can range from about 10 to the 7 to more than 10 to the 13 Gauss, which very strongly impacts the accretion flow and therefore is also expected to impact the jet properties and jet formation. In addition, we can directly measure the spin of the neutron star, so know the spin of the compact object, which helps us to try and test if there's any correlation or relation with the power of the jet in these systems. Neutron stars in X-ray binaries also tend to reside in systems with very wide varieties in donor type, binary orbital properties, and evolutionary stage. While finally, the solid stellar surface of the neutron star brings with it a bunch of associated phenomena, such as, for example, very energetic thermonuclear bursts. All in all, this means that we can use neutron star X-ray binaries to probe the effects of spin and magnetic field on jet formation, to see if there's any influences of donor type, binary properties, and even to check if there's any effects of the ambient material on jet propagation, jet properties, and emission. The main advantages of doing this with next generation facilities, such as the SKA, the ngVLA, comes in 4 different flavors. As you can already imagine from what I've said about these systems being radio faint, is that the main advantage will be sensitivity. We can reach incredibly high sensitivities in 1 hour, up to a factor 5 to 25 better easily than what we can currently do, which really allows us to target faint targets, low accretion rates, and will also enable the performance of timing and burst studies at high time resolution. We will also get a broad spectral coverage that will help us with spectral index measurements. We will get coverage on both the northern and the southern sky when both arrays are active, which is of course important to monitor transient systems. And finally, the UV plane coverage is so good that we can again go to very high time resolution in order to study these systems. This, in my opinion, really allows for 4 next things, and new things or things that we can do better for neutron star jets. And specifically, one for neutron star jets is that we can really study their behavior at low accretion rates, but we can also use neutron stars to look at jet modeling and jet launching in 2 complementary ways with more ability. One of those is to try and see if there's any scaling, as I said, between the jet power and the compact object properties. And the other is to really probe the structure, the emission profile, and the velocity profile of the jet. Finally, we can also use these new arrays to actually see how these jets interact with surroundings, both inside the system and outside of the binary system. Now, these have all been very general. I'll go into this in a bit more detail, but before I do so, I'd like to remind you of different types of X-ray binaries, because the way we do this will be a bit different for these different types. So to do that, let me very quickly go back to this X-ray radioluminosity diagram. In this version, you see 3 different types of neutron stars in X-ray binaries. The gray circles are low mass X-ray binaries. The red points are persistently accreting high mass X-ray binaries. And the blue and purple points are transiently accreting high mass X-ray binaries. To make that a bit easier, there's this schematic version that you can make of the diagram. And basically, again, we have these 3 source classes that we can focus on. What's important, however, to note is that not only the donor star is different between these systems, but also the neutron star tends to be systematically different in its properties. So low mass X-ray binaries tend to be all systems with a fast spinning but weakly magnetized neutron star. The systems with massive donor stars are obviously much younger, as the second star hasn't gone supernova yet. This means that they tend to spin slowly but are typically much more magnetized. So let's go through these categories one by one. Let's start with the low mass X-ray binaries. The main advantage there, as I mentioned before, will be that we will be able to probe these systems at their lowest accretion rate states and all the way down to quiescence. Currently, we know that there is an X-ray radioluminosity coupling and inflow-outflow coupling above about 1% of the Eijnden rate, but it's very difficult, very challenging to probe this when we go to lower mass accretion rates. There are some hints that possibly this correlation may steepen when we go to these very low accretion rates, but currently without detections in radio in that regime, it's very hard to say. Now, what we can do with this higher sensitivity is probe this X-ray radio coupling down to quiescence as a source comes out of quiescence into outbursts and then decays again. We can also search for the onset of, for example, the radio propeller regime, and we can also track the accretion efficiency by seeing if this correlation has the same shape across the entire range in X-ray luminosities. As we do so, another thing that we will be able to access using mostly this very wide bandpass with both arrays is to actually get a better handle on the spectral evolution. While for black holes, this is quite well known how this structurally changes throughout outbursts, for neutron star low mass X-ray binaries, this is much more sparsely sampled and much poorer known. So we don't have the same overall schematic picture of what the structure and the spectral shape of the jet is doing throughout an outburst. Having this high sensitivity in combination with a wide bandpass will really help us understand that. A very exciting new opportunity in my mind is that we can try and time the radio jets from neutron star Lomas X-ray binaries as well. This is a technique that has been pioneered in the past couple of years for black hole X-ray binaries. You see an example of that here on the left for MaxCJ1820, which is work by Alex Seftarenko et al. And what you can see is that across a wide range of different radio frequencies, it's possible to actually produce power density spectra from the radio light curves. This is something that's currently completely beyond the realm of possibility for a typical neutron star Lomas X-ray binary, but with the enhanced sensitivity from these new arrays, for a typical neutron star outburst, you would be able to create a similar signal to noise power density spectra. What these in practice allow you to probe are things like the jet speed, the jet internal structure, and the emission profile of the jet through then modeling of why this variability arises and how it's propagating throughout the jet. The opportunities that we will get for transient HIMARS X-ray binaries are actually quite different from the Lomas X-ray binaries. And the main question when we look at transient HIMARS X-ray binaries can focus on what is actually powering the jet. The models that can explain the jets from these strongly magnetized neutron stars and transient HIMARS X-ray binaries predict quite a clear coupling between the spin and the magnetic field of the neutron star on the one hand, and the power of the jet on the other hand. These are also two properties that we can very nicely measure in HIMARS X-ray binary systems. The spin, of course, just as we can for any other neutron star, and the magnetic field through cyclotron lines in the X-ray spectrum. However, currently, it's been very hard to see if there's any correlation with these properties within the sample of transient HIMARS X-ray binaries. We currently have 3 of these systems where we are able to monitor them in radio throughout an outburst. And these are detected at relatively low signal to noise. So the differences between these sources, which may be quite subtle in their jet power and their resulting jet luminosity, haven't shown up very clearly in our monitoring yet. With higher sensitivity again and better spectral coverage, and therefore better determining of the actual total luminosity of the jet, we will be able to probe this in much more detail. For persistent HIMARS X-ray binaries, this will not be the main question. For persistent HIMARS X-ray binaries, I think currently the main open question is why they are actually relatively radio bright compared to their transient counterpart. So if we go back to the schematic that I showed before, we expect maybe naively that the transient and persistent neutron star HIMARS X-ray binaries are relatively similar in radio brightness, simply because their neutron stars and mass accretion rates tend to be relatively similar. However, the neutron star HIMARS X-ray binaries that are persistently accreting tend to be radio brighter, and it's quite unclear why this is. With the XKA and the next generation VLA, there's a couple of approaches to try and probe this. For example, using their broad frequency coverage to try and disentangle possible stellar wind contributions in the spectrum, timing studies to really probe any of the physics and the particle acceleration properties of any non-thermal emission processes that may occur in addition to jet emission, and better sensitivity, of course, to sample more of these sources than just the tip of the iceberg that's been explored so far. Now, finally, I want to briefly finish by a couple of future new science cases that are currently not possible or at the edge of what is possible, but that will be much easier when we go to these new arrays. When we look at Lomas X-ray binaries, there's 2, I think, very exciting opportunities that are currently at the level of pilot studies, but that will be much more accessible with these new arrays. The first is eclipse mapping, where you use the presence of a donor star, which eclipses part of the jet for certain inclinations, and use that to try and map out, again, the velocity and the emission profile of the jet. This is something that's currently been done in pilot studies with the VLA by Ali Petty from Texas Tech. But as I said, this is currently at the edge, really at the forefront of what's possible with current arrays, but will become much more accessible with next generation facilities. Another way to probe the structure and the velocity profile of the jet is to see how they respond to thermonuclear bursts on the surface of neutron stars. We already know that the inner accretion flow very strongly responds, and the question is what the jet is doing in response to that. There's again current pilot studies led by Tom Russell and Anthony Degener using ATCA, and again, this is really at the edge of what is possible right now. With higher sensitivity and especially better ability to do time-resolved studies, this will become a much more standard approach. For HIMARS X-ray binaries, again, there's a couple of things we can do. If you're interested in super fast X-ray transients, we may be able to go and track their X-ray flares in radio at the same time. But we can also start to access extragalactic systems. So the very large sample of high-mass X-ray binaries in the small and large Magellanic Cloud, for example, or to actually look at ULXs in even further away galaxies and try to disentangle between black hole and neutron star systems using their expected radio brightness. Finally, we can try and use these telescopes to see what the impact of these systems on the ISM is. This is something that we can already see happening with, for example, a telescope like Meerkat, as in SKA precursor. This is something we hope to see much more often in the surroundings of neutron stars as well. This is also something that may not have been as expected to see with Meerkat as we see it for X-ray binaries there. And that reminds us that, of course, there will be hopefully a lot of very exciting new types of science that we can do for accreting neutron stars that we didn't actually expect at all before the array was built. Now, throughout this talk, hopefully I've convinced you that neutron star X-ray binaries are very interesting systems to study jet physics for a variety of reasons, and that these new arrays will give us a wealth of new approaches to study their jet properties and to also learn more about jets in a much more general context. I'm just going to leave you here with this final slide that has the main takeaway message of my presentation, which is that we will get a wealth of new opportunity to understand neutron star jets across binary types, pulsar spins, magnetic fields, timescales, and luminosities. My contact details are on the slide. I'm very happy to answer any questions on there or through Slack. And for now, I'd like to thank you for your attention.
All right, we have a couple minutes for questions, and then we'll have to move on. Okay, I see one in the back.
Hey, Jakob, thanks for a great talk. I was wondering if you can comment on how self-similar the physics of these jets is and how well these lessons learned extrapolate to like lower energy systems and AGN.
Thanks, that's a good question. Can you hear me well? Is this working?
Yeah, I can hear you very well.
Oh, perfect. Yeah, I think that's one of the big questions. I think for neutron stars, it's actually quite hard at the moment to make a very definitive statement about that, because we do have quite limited information on them. So I mean, one thing I very immediately think of when you ask that is what I've shown, the correlation between inflow and outflow that you see in these systems, which is something we've also seen in black hole systems across a very large mass scale, for example. I think that's where the comparison to AGN comes in. I think another comparison is that you can make to, for example, white dwarf systems, accreting white dwarf systems that sometimes launch jets and radio flares, where in fact, if you look at the types of accretion flow and the sort of distances where the white dwarf truncates the accretion flow and the jet is being launched from, those are quite similar to the high-mass X-ray binary systems, where the neutron star has such a strong magnetic field that it truncates and sort of interrupts the accretion flow at very large distances from the pulsar itself. So in that sense, I think from that comparison with a lower energy system, if you could call it like that, there is definitely physical similarities, but with the current data, it's very hard to see to what extent they are similar. So I think this is one of those points where actually measuring the jet properties in a much more quantitative way will help us to make those comparisons beyond saying that there's a scaling in X-ray and radioluminosity that looks similar.
All right. We are out of time, so let's go ahead and thank Jakob again.